we have Q1 and Q2. And Q1 is double Q2, Q1 is positive, Q2 is negative. We draw bars to represent the approximate value of the electric potential. Now, do you know the equation for electric potential?
Yeah,
KQ over R. So we're going to be taking point A as a standard. Okay, so let's see what that means. Let's find the voltage by Q1 at point A to see what that means. And that will be K Q1 over distance. Let's find the voltage by Q2 at point A. That would be K times negative Q. And how far is Q2 from point A?
1D.
No. 4D minus D.
Oh, Q2.
3D.
3D, yeah.
Now let's add them up. So 2KQ over D minus KQ over 3D. So 2 minus a third is 5/3. So that's the voltage at A. It's 5/3. This is 5/3. Okay, how about the voltage at point B? Point B, point B. How far is Q1 from point B?
2D.
Nice. And how far is Q2 from point B?
Q2.
Yeah,
2.
also 2.
Yeah.
So you're going to have 2KQ over 2D minus KQ over 2D. Now 2 over 2 just means a 1. So KQ over D minus half KQ over D means a half. So now your voltage dropped to a half, right?
Yeah.
So maybe somewhere like that will do. Maybe a bit more.
Yeah.
Okay, so this should be a half. This should be 5/3.
You have to find point C as well.
Yeah, now point C. So, how far is K1 from point C?
3.
3D. And how far is K2 from point C?
1.
Right. So we're going to have 2 over 3 KQ over D minus KQ over D. So that's going to be 2/3 minus 1, which is a negative third. That means we have to go under the x-axis, right?
Yes.
And negative third is less than half. So we're going to make the box a bit smaller. Okay, that was part AI.
Yeah, double A.
Do I have an expression for delta V CA, which is the potential difference between point C and point A in terms of these things? So look, delta means minusing, right? So delta V CA is equal VC minus VA. Now, the voltage at C and the voltage at A are both caused by two charges. That means now we must write 4 different voltage equations. Does that make sense? Let me bring up the figure. So let's find the voltage at C. Of course, you must show all the work. So K, Q1, and how far is Q1 from point C?
Q1 from 3D.
Uh-huh. Plus K, Q2, and Q2 is how far from point C?
Just D.
minus K 2Q. How far is Q1 from point A?
1.
K times negative Q. How far is Q2 from point A?
3.
3D, right?
Mhm.
Okay.
Yeah.
Let's do it. Uh, so we're gonna have to combine those. So we're gonna have 2KQ 3D minus KQ D minus 2KQD plus KQ 3D. 3D here, 2KQ minus 3KQ minus 6KQ plus KQ. So 2 minus 3 is negative 1, minus 6, negative 7, plus 1,
I lost track.
negative 6 KQ over 3D, which then becomes negative 2 KQ over D.
Wow.
Yeah. Okay. Let's move on to this part. So, triple I, a proton is released from point A. You have an expression for the kinetic energy of the proton when it reaches point C. So from point A, it will go to point C. So the change in the KE is equal to the negative change in the potential energy. This is just a fact that you have to know. And the change in the potential energy means Q change in voltage. Now, to go from point A to C, we already found it to be negative 2KQ over D. So minus Q instead of delta V, put negative 2KQ over D and becomes 2 K small q capital Q over D. And of course, right now we are dealing with an electron, right? So I'm going to change the smaller q, which is the electron's charge, for E. E for elemental charge.
Isn't it a proton released?
Oh, sorry, proton.
Yeah.
Yeah, proton electrons have the same elemental charge, it's just E. Good.
That's it?
Mhm.
Okay.
Good. Okay, let's see what's next. Indicate whether there is a location on the x-axis between spheres 1 and sphere 2 where the electric field is 0. So look, the Q1 is positive, and the field will leave the positive charge.
And go to the negative one.
Right. And go to negative charge, and the negative charge will be receiving an electric field. So in this case, both fields are going the same direction. They will always add up, they will never cancel. Because ultimately field is a vector. So it doesn't care about the sign, it cares about the direction. Right now direction is the same, they will never be 0. So,
That's the answer?
well, yeah, we're going to say no. No place. No place on the x-axis, right? Okay. Or it's going to be 0, basically. Why? Because the electric field by the Q1 heads to the right, and the electric field by Q2 also heads to the right. Okay, and so the fields, the electric fields, point in the same direction, so they add up, will never cancel. Sample of molten atomic ideal gas is sealed in a container with a movable piston. The container is thermally conducting and is held in a water bath. The gas is initially at state 1, and an external force makes the piston move very slowly until the gas reaches state 2. The gas is then brought to state 3 and finally back to state 1. The dot below represents the piston during the process 1 through 2. Okay. On the dot, draw and label the forces, not components, that are exerted on the piston. Okay, so what are the forces that are happening?
One is going up.
The gas is in the piston, right?
Yeah.
And the gas always pushes up.
Yeah.
What's pushing down on the gas?
The gas, the piston.
Does the piston have weight?
It says movable. Doesn't mention weight, I think. No.
We're going to assume it has weight because pistons always have weight. They always do. It's either a block or a piston. So the okay, so we're going to say the F of the weight of the piston, right? The force of the weight. What else? The force by the atmosphere and the external force. Now, how do we know if that points up or points down? Because it's going to make it from point 1 to point 2.
Yeah.
Will the volume go up or go down? Go down. So it's going to be compressing it. So the external force. Okay. Now you must draw 3 arrows that in total add up to this arrow that we just drew, going upward. So you're going to have
Three tiny ones.
3 tiny ones, exactly. That are, let's say, same length as each other. So I'm going to say F atmosphere, F weight,
And external.
piston, and F external. Okay. Derive an expression for Q23, which is the heat transferred by heating or cooling from 2 to 3. That is an isovolumetric process, right? So the work is 0. So delta U is equal to Q plus W, but delta V is 0. So work is 0. So delta U is equal to Q, and I think you know that delta U is equal to 3 over 2 nRT, but now T is actually changing, right? Okay. So delta T means T in state 3 minus T in state 1. But the problem is that the question said make your answers in terms of PO and VO. So we're going to say that PV is equal to nRT. So I'm going to replace nRT3 T1 with P3. I'm sorry, it should be T2. With P3 V3 minus P2 V2.
Okay.
So I'm going to say 3 over 2 P3 V3 minus P2 V2 is equal to Q. Now, how much is the pressure at point 3?
P.O.
Let me just get the figure. So in point 3, the pressure is PO. In point 3, the volume is VO. In point 2, the pressure is 4 PO, and the volume is
Same volume.
VO. So 3 over 2 times negative 3 PO VO, and you get negative 9 over 2 PO VO as the answer. So sketch processes 1 to 2 and then 2 to 3 on the pressure temperature diagram in figure 1. State 1 is indicated in diagram. Label state 2 and state 3. So let's go back and see what's going on. So in state 1, we had PO slash 4VO. In state 2, we have 4PO and a VO. And in state 3, we have a PO and a VO. Okay, that's what we have. Let's take that information to the question. Okay. So right now we're at state 1, which is a PO and a 4VO. But then in state 2, the PO becomes 4 times larger, correct? So we're going to go all the way to 4PO. Like this. We're going to label this as state 2. And then in state 3, we're going to have to go back to PO, VO. Okay. Now we know that PV is equal to nRT. And the volume is constant. And so P is going to be direct with temperature when the volume is constant. Meaning, as we go from state 2 to state 3, and as the pressure goes from being a 4PO to a single PO, that means our temperature has to drop by 4 times. So right now, at this scale point, we have T1. That means at this scale point, we have 4 T1. At this scale point, we have half T1. At this scale point, we have 3 over 4 T1. We're going to have to go back all the way to 1/4 of a T1, which is here. Okay? Which is state 3. So that's how we do it. D. If during process 1 to 2, the piston was pushed quickly instead of very slowly, and underwent an adiabatic compression. Now you should know that adiabatic means the Q is 0, and compression means the delta V has decreased until the pressure reaches 4 PO at the new state. Okay, so indicate how the line or the curve for process 1 to 2 would be different, and then justify your answer. So what's happening here is that delta U is equal to Q plus W. But we were already told that we have an adiabatic compression, which means that Q is equal to a 0 if it's adiabatic process. So delta U is equal to 0 plus W. So delta U is equal to W. Now W is equal to negative P delta V, and since we have a compression, that means your delta V is going to be negative. So negative on the outside with negative on the inside gives you a positive work. So since delta U is equal to work, delta U will also be a positive number. Okay. So since delta U is positive, that means that temperature will increase. And right now, if you look at state 1 to state 2, the temperature is not increasing. From 1 to 2 is just a vertical line, which is temperature is constant, but now it's actually going to be increase of temperature. And we still have to reach 4 PO. So that means that our new line will look like this. Curved and to the right. So you must still reach 4 PO, but your temperature now must be more than temperature 1, essentially. So that means that, so the line isn't vertical anymore. It has to point up and to the right of the original state 2. Students are given a glass block that has been treated so that the path of a beam of light can be seen as the beam travels in the glass. They're asked to determine the speed of light in the glass. Describe the procedure that would collect the data to allow the students to collect the determine the speed of the light in the glass. So let's just think about the equation that we actually have to incorporate here. So N is equal to C over V. Okay. And we simply know that C is a constant, but V is going to be unknown. Okay. And N of the glass is also unknown. So right now we have two unknowns. If we can find the N, we can therefore find the V. Which reminds me of Snell's law of N1 sine theta 1 is equal to N2 sine theta 2. Okay, where the N1 sine theta 1 is the incidence, while the N2 sine theta 2 is the refraction. And right now we're looking to find the N of the glass, which is the N of the refraction. And we know that the light is coming from the air, and the N1 of the air is just a 1. So that's gone. Let's call this sine of theta I and sine of theta refraction. We can now find the N2 by plotting them against each other. Okay. And so we are able to change the sine of theta I, which will then result in a change in sine of theta R. Okay. So if you are able to change sine theta I, that's going to be your x-axis. And if the result is going to be seen on the sine theta R, that's going to be your y-axis. Okay, so now it's like saying y is equal to mx, where the y is the sine of theta r, where the x is the sine of theta I, where the slope is the index of refraction. Actually, wait, sorry. No, I made a mistake. Okay, 1 second. So we're going to say sine of theta r is equal to, bring the n2 down, sine of theta I. So essentially it's like saying y is equal to mx, and here we have sine theta I times 1 over n2. So the y-axis is going to be the sine theta r, and the x-axis is going to be the sine of theta I, while the slope is going to be the reciprocal of the index of refraction of the glass. Now, of course, so far you're not getting any points, right? Because all this scribble is for you. You're supposed to be doing the scribble on the piece of paper they give you in the exam if they give you A4. They must give you A4 to like write on and stuff. Right now, let's start with the procedure. So we don't need any of this right now. That's just a thought process for us. So now what do? We're going to shine light on the glass. But of course, you have to on the glass's side with an angle that is obviously not 0, with an angle that's more than 0. Of course, the angle reference here is with the normal, right? So this is the glass, and that's the normal line. When I say more than 0, I mean it should not be like this. No, it should be like this, like this, like that, like that. Because the angle is measured to the normal, basically. Okay, so with an angle that's more than 0, okay, relative to the normal. Okay, and of course you're gonna measure that angle, right? You're gonna measure the theta I, which is the incidence angle, okay, and the theta R, which is the refraction angle, using, what do we use for measuring angle in math classes? It's like that semicircle thing.
Yeah, I don't know.
It's called protractor.
Yeah.
It's called a protractor. Okay. Now, of course, having one measurement is not going to be enough. It's always best to have 5 measurements. So you're going to say change the incidence angle and measure the refraction angle for 5 different measurements. 5 measurements will actually do. Okay. So yeah. Now, it says describe how data collected in part A can be used to produce a linear graph. Well, like we said, we are able to change theta I. So now if we invoke the Snell's law, n1 sine, or ni sine theta I is equal to n refraction sine theta refraction. If you're able to change something, that puts it as the x-axis. And we're going to say since n1 is the n of the air, it's equal to 1. So the equation becomes, okay, let's see, sine theta I is equal to nr times sine of theta r. So we're able to change the incidence angle. It's going to be the x. So we're going to put it on the other side. We're going to say sine of theta r is equal to 1 over n refraction times sine of theta I. So y is equal to sine theta r, x is equal to sine theta I, and the slope is equal 1 over nr. So the reciprocal of the thing. And now, once we have, okay, so by finding, I need actually more space, by finding nr, you apply the equation n is equal to c over v. So nr is equal to c over v. So v is equal to c over nr. Is that good? In a different experiment, the students are given a converging lens, which looks like this. It's able to produce a real image and also a virtual image, depending on distance of the object from the lens. The students are asked to determine the focal length of the lens. Okay. They collect the data shown in the table. Right. CI, identify what measured or calculated quantities could be graphed to yield a straight line that could be used to find the focal length of the lens. Now, I think you should know that the equation of the lens is 1 over f is 1 over SI plus 1 over SO. Okay. And so we are able to change the SO, which is the object distance. So we're going to say 1 over SI is equal to 1 over F minus 1 over SO. Okay. So essentially, this looks like a Y is equal to mx plus b. Okay. And so basically the y is the 1 over si, and the x what you're able to change, right? Which is the 1 over so, and the slope is negative 1 most likely, and the b is 1 over f. So the b is the y-intercept, which we call in physics the vertical intercept. Okay. So basically, the vertical axis is going to be 1 over si, which is the y-axis, yani. Horizontal axis is the x-axis, which is the 1 over so. And the y-intercept, the reciprocal of it, is going to be the focal length. Okay. Now, use the blank columns in the table to list any calculated quantities you will graph other than data provided. Well, you're supposed to be graphing 1 over si and also 1 over so, correct? So we're going to have a column for 1 over so. We're going to have a column for 1 over si. And we're going to have to use the calculator to actually find these values. So, for example, for the first one, I got 3.3. Second one, I got 4.0, 5.0, 6.6, and 10. And for the 1 over si, we do the same thing. So 17.2, 16.1, 15.3, and 12.9,
Last one's 8.3.
8.3. So now we got our variables, okay? And now we can probably take them to plot in the next part. So let me go ahead and take our data. Okay, so now we got our data. We have the 1 over SO on the x-axis. And by the way, let's just go back and write the unit, right? So if you do 1 over meter, that means you get meter to the power of negative 1. Meter to the power of negative 1. Okay. So now here, 1 over the SO, which is the meter to the power of negative 1. 1 over SI, meter to the power of negative 1. Now, if you look at the 1 over SO, it's ranging from 3.3 all the way to a 10, correct? So now, if I make this into a 2, a 4, a 6, an 8, and a 10, then I should be fine. Okay? Okay. And the same for the y-axis. We're starting at least number is 8.3, most number is 17.2. So now I guess I can make, I think I made a mistake in the calculation. Or I'm fine. No, I'm fine, right? Yeah, my math is right. Okay, so 8.3 all the way to 17.2, right? So what division points can we use? Like a 5, and a 10, and a 15, and a 20, 25, and a 30. As long as you cover 1/2 of your graph, you're fine. Okay. Now for the 1 over SI, okay, it's time to actually start plotting, right? So 3.3, 17.7. So this is a 3 right here. So a 3.3 would probably be somewhere there. 3.3, which is here, with 17.2. This is here 17.5. So 17.2 is probably going to be a bit less. Maybe like here. Let's see where they meet up. They're going to meet up here. Okay. They're going to meet up there. That's the first point. The second point, 4 and 16.1. 4 and 16.1, which is probably going to be here. Let's actually be careful here. So how many ticks do I have? I have 1, 2, 3, 4, 5. So each tick is a 1 point, right?
Yeah.
So now I have 16.1. That means I'm looking at the second tick.
Yeah.
So 4 and 16.1 would actually be here. Next up, 5 and 15.3. So 5 and 15.3 somewhere here. Next up, 6.6 and 12.9. So this is a 7. That's 6.6 and 12.9, which is here. Okay, next up we have 10 and 8.3. 10 and this is 7, this is 8. 8.3 is going to be there.
It's 6.6. Why is it exactly on the 6?
Wait, no, 8.3 for the y-axis.
Oh.
6, 7, yeah, we're good. Okay, now what do? I must try to connect them with a single line. I must try. It doesn't mean I could, but I will put a straight line that will go either through them or at least between them. And I think that's the best fit line. That's why it's called best fit line. You never can hit all the points, but you just have to best fit it. That's the best fit line. Okay, best fit line. So that's what they said. They said draw it, which we did. And now they're saying to calculate the value of the focal length. Like we already said, the reciprocal of the y-intercept, which physics will call it vertical intercept, same thing, is the focal length. So now you should go and you should see where the graph was hitting the y-axis, and you should just reciprocate that. Okay, so at what point is the line hitting the y-axis? That's like a 21.2, right?
Kind of, yeah.
Yeah. So this point is like a 21.2. You don't have to be super accurate. So the reciprocal of it is going to be 1 over 21.2 is the focal length. Okay. So the focal length is equal to, we should just now use a calculator and find out what that is. We'll get 0.047 meter. So we're good. All right, in scenario 1, a rectangular loop of wire with width of W and length of L is initially inside a region of uniform magnetic field of magnitude B, directed out of the page, because dots mean out of the page. The loop is then pulled at a constant velocity to the right. Now, of course, if you are going to be pulling the loop out of the magnetic field, you're simply inducing an EMF. And since we have the velocity here, we're going to say EMF is equal to B times L times V. Okay.
Yeah.
But we're also going to be invoking a different equation, possibly, which is the EMF is equal to change in the flux over the time. And the change in the flux is equal to the magnetic field times the change in the area.
So
What's the change in the area? Is the width changing? No. But the length is changing, right? Because the length, one time it was, the whole length, now it's going to be zero length outside. So the length is changing. So now we're going to have width times, the width is not changing. So B times width, which is not changing, but the length is changing. Okay, so keep that in mind. Now, anyways, while the loop is being pulled, an EMF1 is induced in the loop. Okay, we get that. In scenario 2, which is identical to scenario 1, except the loop is now rotated at 90 degrees. The loop is again pulled at a constant velocity to the right until it's fully outside. So the same scenario here, the same idea, we're going to get induced EMF. But this is called EMF2, and this is called EMF1. And as of this moment, we're not being asked anything. Maybe they're going to ask us to compare them, right? So let's see. Indicate whether EMF2 is less than, equal to, or greater than EMF1. Okay. So let's just invoke the EMF equation in our answer. Okay. So EMF is equal to change in the flux over time. And like we said before, change in flux means B times the width and delta, whatever is changing, so the length basically, over the time. Okay. How does that help us? Now, the B is the same, right? What is different between the two?
The length.
The length. So here, this amount, so this is the vertical height in scenario 1, and that's the vertical height in scenario 2. The vertical height is going to be more in the case of scenario 2. So the vertical height in figure 2 is more. Okay. And since the change in the flux is proportional to the vertical height, so more height equals to more change in flux, which equals to more EMF. So EMF of figure 2 is more than EMF of figure 1. Yeah. B. The loop has a wire whose resistance is R. Derive an expression for the current I1 in the loop as being pulled out of the region of uniform magnetic field in scenario 1 in terms of R, B, V, L, and W. So, look, the EMF is equal to the change in flux over the change in time with an absolute value. So if it's decrease or increase, EMF will always be positive. Now, as we said, the width is not changing, right? But the vertical height is. Okay. So this part here is the one that is actually changing. Okay. So now we're going to say B times width times the change in the length over time. And the change in the length over time is just the velocity. So B times W times the velocity. Okay, so I guess we can now state a pattern that if the velocity is pointing in the x-axis direction, the dimension that is also pointing in the x-axis direction will be used to find it. So essentially, velocity is equal to change to the length. Why? Because the length is parallel to it over the change in time. We had a similar question in the MCQ. We did the same thing. So yeah. Now let's see. So now we have all the information that we need, and essentially V is equal to I times R, and so I is equal to EMF over R. This is I of the first loop, so I1, and the EMF is just B W V over R. So yeah, okay. So now they said make it in terms of R, which we did, in terms of B, which we did, V, which we did, W, we did. Only L we did not because the V took care of that. So they might say make it in terms of all of these. It doesn't matter. Like it doesn't mean you should put all of them, but like most of them will go in there probably. Okay. C. A student claims that in scenario 2, the induced current in the loop could be equal to E1 if the loop is pulled with a greater speed. Indicate if that student is correct or not. So, look. So in loop 1, we have I1. In loop 2, we have I2. Which one do you think is bigger as of now? Which one has more vertical height?
The second one.
The second one.
Yeah.
So here, loop 2 has more vertical height. So it already has more EMF. It already does. So already we know that I2 is bigger than I1. And now imagine if you give the loop in the second one, loop 2, more speed. You're going to even make I2 bigger than I1, right?
Yes.
So right now,
Not gonna be equal.
exactly. So they're already not equal. And now if you make the velocity larger, they're going to be further not equal. So the claim is going to be wrong. Okay. So we're going to say what? We're going to say that loop 2 EMF is larger than loop 1 EMF at the current velocity, since the vertical height is larger in loop 2. So putting more speed in loop 2 will further enlarge I2, making it even more now than before. Okay. So, yeah, very good. And if you want, you can always invoke this expression, I is equal to BWV over R. Since I is equal to BWV over R. So more speed leads to more current.